Last time we talked about fundamental and derived physical quantities, and now we will consider how to express the results of measurements of these quantities. The first figure of merit we talk about is the order of magnitude. So how do we determine the order of magnitude for a physical quantity? Well, the first thing we have to do is express the number in scientific notation. So this is in powers of 10. For example, if we have a number 6,340, let's say, this is going to be expressed as 6.34 times 10 to 3. So we leave only one digit before the decimal point. So this is our strategy. And then we look at the multiplier. If the multiplier is less than square root 10, 3.162, the power of 10 will be the order. For example, let's say we find 2 times 10 to 2. If we check the multiplier, it's 2. It's less than 3.162. So we can see that this is going to be 2 orders of magnitude. On the other hand, if the multiplier is greater than square root 10, 3.162, then we add 1 to the power of 10. So if we have 5 times 10 to 2 as our answer, because the multiplier 5 is greater than 3.162, we add 1 to the power, so we have 3 orders of magnitude. Let's say that we have measured length and the result is 0.0086 meters. So to express this in scientific notation, we leave only one digit before the decimal point. So it's going to be 8.6 times 10 to minus 3 meters. We check the multiplier, 8.6, it's greater than square root 10. So this will be estimated as 10 to minus 2 meters, and it's 2 orders of magnitude. So similarly, minus 2 orders of magnitude. If we have a 0.0021 meters, it will be 2.1 10 to minus 3 meters, and this will be approximately 10 to minus 3 meters. 2.1 is less than square root 10, therefore we will say this is minus 3 orders of magnitude. So this is how we come up with orders of magnitude for the results of the measurement of a physical quantity. Now, when we do a measurement, we are not 100% sure about the result. There is always an uncertainty. And how do we express this uncertainty? So if you read a report and basically the experimentalist reports a length to be 6.0 centimeters, what this really means is it's 6.0 plus or minus 0.1 centimeters. So the last digit that we leave at the result, this is basically pointing to where the uncertainty is. So this is the digit where we have the uncertainty. So this has two significant figures because there's the 6 and 0, so we're using only 2 digits, so we have 2 significant figures. If we have the report of a mass 1.50 times 10 to 3 grams, so because we have 3 numbers here, 150, we have 3 significant figures, and the last digit, 0, is basically where our uncertainty is, so we have 1.50 plus or minus 0.01 times 10 to 3, of course, grams as our result. And if we have this measurement basically reported as 1.500 10 to 3 grams, then the last 0 is where our uncertainty resides. So this will be 1.500 plus or minus 0.001 gram, 1 times 10 to 3 grams. So this is basically, because I have 4 numbers here, this has 4 significant figures. So that's how we deal with the uncertainty, or that's what the numbers mean when we report it for a measurement. So, well, we have to do algebra with these numbers, so in order to calculate certain other physical quantities, and the rules are as follows. In multiplication and division, we keep the smallest number of significant figures. Okay, so let's say that this length measurement was really a radius measurement. It's 6.0 centimeters, and we're trying to calculate the area of the circle, which is pi r square. So we have two significant figures in the radius, and we have pi, which can have many digits after the decimal point. So we're going to keep only two in our answer. So our answer is 1.1 times 10 to 2 centimeters square. So we only keep two digits. In addition and subtraction, we also keep the smallest number of decimal places. So we're adding two physical quantities, two lengths, let's say. One is 23.2, so it has uncertainty in the first digit after the decimal point. And one is 5.174, which has uncertainty in the third digit after the decimal point. So we're going to keep only three significant figures here. So this has three, this has four significant figures. If we add these numbers, it's going to be 28.374. But since we are required to keep three significant figures, this will be rounded to 28.4. So, and this is basically telling us that our uncertainty will reside in this digit after the decimal points. Okay, so as you can see, when we do these operations, we have to round the numbers in order to get the correct number of significant figures. What are the rules of rounding? If the last digit dropped is greater than 5, last digit retained is increased by 1. So here's the example, 1.346. This is the result of our calculation, let's say, and we want to have three significant figures. So what we need to do is to drop this 6, but because 6 is greater than 5, we're going to add 1 to the last digit retained, which is 4, so it's going to be 5. Therefore, this will be reported as 1.35. If the last digit dropped is less than 5, then the last digit retained remains unchanged. So if we have 1.343, we are required to have three significant figures. We drop 3, but we check if it's less than 5. It is. Therefore, the last digit retained remains the same. It's going to be 1.34. If the last digit dropped is exactly 5, then the last digit retained is rounded to an even number by adding 1. So here is the answer, 1.345. We're going to drop this 5. We're required to have three significant figures. So we check if the last digit retained is even or not. It is even, therefore we don't change it. So this will be 1.34. But when we have this result, 1.355, we drop the 5, we check the last digit retained. It's 5 and it's odd, therefore we have to add 1 to it. So it's rounded to an even number, so it becomes 1.36. Okay, so this is basically how we round the numbers when we do algebra with physical quantities, and the physical quantities have an uncertainty embedded in them, and the uncertainty information is in the last digit after the decimal point, and the total number of digits that we report is called the number of significant figures, and we're always required to maintain the smallest number of significant figures in the final answer of our calculations. And for physical quantities, we report an order of magnitude, and this is found by checking the multiplier when the number is expressed in scientific notation. If it's less than square root 10, then we read the power of 10 to be the order of magnitude. If it's greater, then we add 1 to it. Okay, now we're going to talk about vectors, and vectors are physical quantities that have a numerical value, a dimension, a unit, plus a direction. So first, let's start with representing a position in space. How do we represent a position in space? So we can use, one choice is to use Cartesian coordinates. Cartesian coordinates are also known as rectangular coordinates. And here we have this point P, and we check its components on x and y axes. X and y axes are orthogonal axes. And if we see that the projection of this point onto the x-axis is x0 and the projection onto y-axis is y0, we report this location in 2 dimensions as point P is located in x0, y0. Alternatively, we can check the distance from the origin, and let's say that distance is r, and we can check the angle it makes with respect to the x-axis in the counterclockwise direction. So this is our counterclockwise direction. And here we are basically using polar coordinates. So the polar coordinates of point P is r and theta. R is the distance from the origin to point P, and theta is the angle between a fixed axis, here is the x-axis, and the line drawn from the origin to point P, and this is measured in the counterclockwise direction, so that's the positive direction for the angle. So we have 2 choices. We can use Cartesian coordinates. We can represent it as x0, y0, or we can use polar coordinates and represent it as r and theta. Now, how do we transform between these 2 coordinate systems? Well, you can see that we have a triangle here, a right triangle here, and if you check cosine of the angle theta, it is x0 divided by r. So x0 is r cosine theta. And similarly, sine of this angle will be y0 divided by r, so it is y0 is r sine theta. So this is how we transform between polar coordinates and Cartesian coordinates. On the other hand, because of this right triangle, we can use Pythagorean Theorem, which says r squared equals x squared plus y0 squared. So we can use r squared equals x squared plus y squared. So here we have the coordinates x0 and y0. And r will be square root of x0 squared plus y0 squared. And as for the angle, if you look at the tangent of the angle, it is y0 divided by x0. So it's going to be tangent inverse of y0 over x0 is the angle theta. So these are our equations, transformation equations between rectangular coordinates and polar coordinates. So let's take an example. Let's say that point P is located at minus 3.50, minus 2.50 meters. Let's find the polar coordinates. So the coordinates are given in Cartesian system, so we have to use this set of equations. From Pythagorean theorem, the r is square root of 3.5 square plus 2.5 square, which is 4.3 meters. And the angle theta, tangent theta, is y0 over x0 minus 2.5 over minus 3.5. That is 0.71. And if you use a calculator, you can see that the angle is either 35.5 or 215.5 degrees. Now, is the angle 35.5 or 215? So if you look at the quadrant that this point stays in, it's basically, let's check our quadrants here. This is the first quadrant, this is the second quadrant, third quadrant, and fourth quadrant. And you can see that here x and y are positive. Here y is positive, x is negative. Here x and y are both negative. And here we have y negative, x positive. So because our answer is basically minus 3.5 minus 2.5, we are definitely in the third quadrant, so the angle cannot be 35.5 degrees. The angle has to be 215.5 degrees. Okay, so when we talk about physical quantities, depending on if they have a direction associated with them or not, we call them vectors or scalars. Now, a scalar quantity is described by a single numerical value with an appropriate unit. It has an appropriate dimension, but it has no direction. A good example is temperature, that's measured in Kelvin. Temperature doesn't have a direction. Volume is measured in meter cubed. Mass measured in kilograms. Speed measured in meters per second. These are all scalar quantities. On the other hand, a vector quantity is described by a number with a unit and a direction. So example is displacement. For example, here, if you go from point A to point B, we have this vector drawn from point A to point B. We show it with an arrow here. And this is the vector D, and we put an arrow on top to show that it is a vector. The magnitude of this vector D is D, numerical value, that's positive, and it has a direction. It points from point A to point B. Now, as for the properties of vectors, let's say that we have two physical quantities that are vectors, and these two vectors are equal to each other. What does that mean? It implies that the magnitudes of these vectors must be equal, and they must point in the same direction. So in the Cartesian coordinate system here, you can see if we have two vectors A and B equal, then they must be pointing in the same direction. So here it's pointing in the diagonal, a 45-degree angle with respect to the x-axis, and they must have the same magnitude. Okay. Now, if you want to add two vector quantities, we can use this head-to-tail method, and we can also work in terms of the components that we'll talk about later. So here is vector A, and here is vector B. So we first draw the first vector A, and we put the head of this vector touching the tail of the second vector. So we connect the head to tail, and then we draw a vector from the beginning of the vector A, so from the origin of vector A to the end point of vector B, that's our resultant vector R. So that is A plus B. So this is for two vectors. If we have four vectors, A, B, C, D, again we arrange them in such a way that the head of the first vector is touching the tail of the second vector. The same story here, same story here, and then we connect the beginning point to the end point to find our resultant vector, which is A plus B plus C plus D, four vectors. Now you can notice that the vector addition is commutative. It has a commutative law of addition. So that means it doesn't matter if you add vector A to vector B or vector B to vector A. You can see this with the head-to-tail method. If I draw vector A first and then vector B, here's the resultant vector. If I draw vector B first, then vector A, here's the resultant vector. It's the same thing, so we have A plus B is B plus A. We also have associative law of addition. A plus parentheses B plus C is parentheses A plus B plus C. So we can show that here is vector A, here is vector B, here is vector A plus B. If we add to it vector C, we obtain parentheses A plus B plus C. This is the vector in purple. Now, if we do B plus C first, so B here, C drawn here, and then we draw vector A, and we go to the beginning and to the end, and we have parentheses B plus C plus A. You can see that these two vectors point in the same direction and they have the same magnitude. Therefore, they must be equal. So we have the associative law of addition. Now, one important thing to note here is that if you want to add two vectors, you cannot always add two vectors. The vectors should be representing the same physical quantity, so they must have the same units. So for example, you cannot add a displacement vector to a velocity vector. This makes no physical sense, so this is not allowed. Okay, so to summarize, in this lecture we talked about how to report the results of measurements of physical quantities. Well, we can talk about order of magnitude, which is given by the nature of the multiplier in scientific notation. We check if it's less than square root 10 or greater than square root 10. We look at the number of digits that are reported for the measurement of this quantity, and the last digit represents the uncertainty. The total number of digits we use in order to represent the quantity is called the number of significant figures, and the rule is that we always keep the smallest number of significant figures in algebraic operations. And in doing so, in keeping the smallest number of significant figures, we have to do rounding. For that, we check the digit that we're going to drop. If it is greater than 5, we add 1 to the last digit retained. Less than 5, we keep the last digit retained unchanged. If it is 5, then we check if the last digit retained is even or odd. If it's even, we do nothing. If it's odd, we add 1. We can represent a position in space either by using Cartesian coordinates or polar coordinates in 2 dimensions. For 3 dimensions, of course, we can use spherical coordinates, cylindrical coordinates, etc., other coordinate systems. So in the Cartesian coordinate system, if the components are x0 and y0 for the projections onto x and y axes, and the distance from the origin is r, and the angle that we make with respect to the x-axis, which is a fixed axis, is theta in the counterclockwise direction. These 2 values, x0, y0, set of values, and r and theta, can be transformed with these equations, and that is basically relying on this right triangle and the trigonometry trigonometric properties of this right triangle. So cosine theta is x0 over r, so x0 is r cosine theta, y0 is r sine theta. Pythagorean Theorem, r is square root of x squared plus y squared, or tangent theta is y0 over x0. And when we calculate when we do this transformation, we find the angle, it may not have a single value, and we have to check which quadrant that we have to be in to determine the correct angle. And we talked about vector and scalar physical quantities. Scalar quantities have no direction, vector quantities have a direction, and when we add scalar quantities, we also should be adding the same physical quantities, so they should have the same unit. And for vectors, when we have the equality of the 2 vectors, we check both the direction and the magnitude. And when we add vectors, one method is to use head-to-tail method. We can graphically add them by connecting the head of one vector to the tail of the next vector to add them up. And we see that a plus b is b plus a. We have a commutative relation, and a plus parentheses b plus c is parentheses a plus b plus c. We have an associative relation, and we should also be careful when doing algebra with the vectors. They must have the same units and represent the same physical quantity. We cannot add a displacement vector with a velocity vector.